Hello class, today we're going to be working on 6.2, other rates of change, which is basically going to be the same thing we did yesterday, except we're going to be using things other than speed. All right, our first example, we're looking at vets. Many vets use a drug called pentothal to put out an animal during an operation, that is, put it to sleep. The graph shows the amount of pentothal required for dogs of different masses. So on our graph here, we have dose of pentothal in milligrams along our y-axis. This is our dependent variable because it depends on how much the dog weighs or what the mass of the dog is. So we see our scale along our x-axis goes up by 0.5, so every other line is our whole number, and our y-axis is actually going up by 5s. So A, find the rate of change, so the number of milligrams of pentothal needed per kilogram. Find the rise over run. So remember our rise, we are using our y-axis, our y-coordinates along the side here. Over a run, we're going along here. So an easy way to remember it is a hot air balloon rises, so it goes up. And when you run, you're going to run along a straight line. All right, so we're going to take two different coordinates. So we're going to go with nice easy numbers. So 1 and 2 for our x coordinates, and then we'll go with our y coordinates from there. So 2 and 31 and 1 and 23. So our rise, again, we're using our y values. So we take our bigger number, 31, and we subtract 23, which gives us 8. And our run, we use our x coordinates, which is, and we again use our bigger one. So 2 minus 1 gives us 1. 8 divided by 1 gives us 8 milligrams per kilogram. Okay, always remember to make sure that we are putting in both of our units there. So we see milligrams there in our title and kilograms there. So milligrams per kilogram. Now, what does this change, or this rate of change, represent? Well, it tells the vet that for every kilogram an animal weighs, the vet must use 8 milligrams of pentothal. So that is a very important thing for vets and doctors to know those different types of rates of change. Our next example is going to show fuel efficiency. So we can see in our title that's going to give us a good hint. So the average fuel efficiency for 2 vehicles. We're going to be looking at an older SUV and a new smart car. So what we need to do first is we need to find the rate of change for each vehicle. So we're going to start with the smart car. And so you can see the line is clearly labeled smart car. And we're going to use 5 and we're going to use 15 for our values, our x values. So we need to find our rise, which is going up and down using our y values. So we have 360 and we have 120. So we're going to subtract 120 from 360, which leaves us with 240. And our run, we have 15 and we have 5. So 15 minus 5 gives us 10. So we would then do 240 divided by 10, which leaves us with 24 kilometers per liter. It means that the car can drive 24 kilometers for every liter of gas in the car. Now we're going to find the rate of change for our SUV. So we're now looking at this line here. So we have 10 and 90 and 20 and 180. So again, we're going to start with our higher number. So 180 minus 90 will leave us with 90. And 20 is our bigger number for our x values, our x coordinates, and 10 for our other x value. So we have 20, subtract 10, which gives us 10. So we do 90 divided by 10, which gives us 9 kilometers per liter. So again, this SUV can drive 9 kilometers for every liter of fuel in their car. Now our next question is, which vehicle is more efficient? That means which one travels further for each liter of gas used. Prove your answer with calculations. That's going to be important, so we want to make sure we always read continuations of our questions. Well, we can see that the smart car is higher, so therefore it can drive further per liter. So therefore, it is the more efficient vehicle. You can go an extra 13 kilometers per liter. So the way we figured that out, we take 24 and we subtract 9, and that leaves us with 13 kilometers per liter. Now remember that the rate of change is a measure of the steepness of a graph. The larger the rate of change, the steeper the graph. So if we were to add another vehicle in here that was for some reason more efficient than a smart car, the line would be steeper, so it would be a higher line up here. Or a less efficient vehicle would have more of a straighter line going, or a horizontal line going down this way below the SUV. So if we saw lines like that, we could say that reasonably we could assume that they would, if a vehicle was more efficient, that this number here, 24, would be a higher number. And if we had another line that was lower, we would know that it would be less than 9 kilometers per liter. So that's what that is saying. So the steepness of the graph, that's what we're looking for. The rate of change can be negative. Remember that we had negative correlations from our last unit as well. So as we can see, our line starts high and then goes low as we go. So let's take a look at this example. The graph shows how height of a small plane changes over time. What's the plane's initial height? So according to this graph here, we see that the initial height is right at the top there. We can see where the line connects in right with our y-axis here, and that's at 1,800 meters. So the plane is already in the air and it is flying. So now we're going to see what is it as it's going down. What's its rate of change as it's going down? So determine the rate of change. So again, we are going to choose our two values. So we have we're going to use 0 and 1,500, and we are going to use 4 and 1,200. Now I know before I said that we always use the larger number, but actually what we do is we are going to be using the one that's further along on the x-axis here. So we're going to start with our 1,200, and we're going to subtract 1,800. So we always use the one further down the line first. So we have 1,200 minus 1,800 gives us negative 600. Notice that we have a negative there. And our run, we are starting at 4, and we're going to subtract 0, which leaves us with positive 4. So if we take negative 600 and we divide it by 4, we're left with negative 150 meters per minute. Now, what does this rate of change tell you about the plane's flight? It tells you that the plane gets 150 meters lower every minute. So that's why it's a negative number, because we are descending. So we are going to have a negative number there. We are not continuing to go up, then we would have a positive number, but we are going down. So 150 meters every minute. And this concludes our examples. Good luck with the work.